Welcome, welcome. Thank you for turning out. I'm gonna put something here up on the screen. It's awesome. I'm sure how much you like to this. Yeah, so kind of okay. So what we're going to talk about today is dimensional analysis, unit analysis, if you will. So from way back in the day, right? I mean, when you first take science courses, when you're in high school or wherever, they beat you to death with the units, right? They say pay attention to units, you miss points if you don't get it right. And then, of course, this leads to all kinds of cruelty where they give you these problems, and this is in kilograms, and this is in grams, and this is in meters, and this is in centimeters, and you have to do all this kind of prestidigitation to get it right. So it just seems like, you know, the units, when I was first taking courses like this, I would be like, units are just kind of, I did it because I had to, but you know, what good is this? Well, I'm going to talk a little bit about what unit analysis can give you. And also, this information essentially, after the Trinity Test and after the Trinity Test, these films were released, these movies, kind of propaganda sort of, were released by the US government, I guess to scare the Russians or whatever it was for. But the yield of the atomic bomb at the Trinity Test was very classified. You're not supposed to know it. And using essentially just unit analysis and some basic assumptions, Sir Geoffrey Taylor, who was a British physicist, were able to watch these. They were equipped with a length here, and just from getting these two different pictures at different times, was able to very precisely calculate the classified yield of the bomb from the Trinity Test, which is well, really kind of amusing. So before we do that, let's do some kind of basics about unit analysis itself. So you have some equations. Equations, these are the bread and butter of the mathematical sciences, physics, right? I mean, force, mass, and acceleration, Newton, energy, potential energy, kinetic energy, and Einstein's famous rest mass business. Now, of course, these all came with units, right? Mass measured in kilograms, some such, and acceleration, right? Meters per second squared, perhaps. MGH, this is mass, and this is gravitational acceleration of gravity. That's a length, right? So these various things have lengths and mass, time in. Where did these equations come from? Right? I used to wonder this. I mean, people just kind of making this up. You know, somebody just guessed this, right? And then they did some experiments and like, yeah, it kind of fits. And so this, right? So, for example, here's a question which kind of gets down to the heart of it. Why is force not F equals mass e to the a? Right? Why not? Have we ever entertained this possibility? Why couldn't it Yes,
I don't think you wanna exponentiate anything with units, so that's.
well, I mean, in a certain sense, that's the bread and butter of kind of the unit analysis, isn't it, right? But can you give me, oh, I hate to do this, but can you give me kind of a principle that something like this, with regard, so you don't want to exponentiate units? Well,
I think
but
of course that you get from the power potential is an exponent. We see power potential.
okay, well, first of all, okay, so we're hearing from the physicists now. This is too good for me. You're beyond my pay grade on this, because what he's saying is, you know, this would grow exponentially with acceleration, and you know, all I'd have to do is toss this chalk and it would fly into atoms, whatever, right? I get that, but there's also another fundamental thing that probably should be the case here, and that is, if you change your units, things should essentially be the same, right? That is to say, if you manipulate this and get a unitless quantity, when you change, so for example, were this to be true, then this equation would be true as well, right? And this would be a unitless quantity, right? So when I change the units on force, or I change the units on acceleration and mass, it should be invariant, right? Because this is unitless, right? And that is kind of a major thing. So let me get, so here's kind of an idea of what might happen. So suppose F is equal to M e to the A. We'll just indulge that at the moment. Okay, so in unit system one, suppose I had two forces. Let's see. And it equals M2 So I've got one mass, one acceleration. So there's my first force. There's a mass and another accelerator. That's my second force. Now in unit system two, suppose I have and X, C.
Oh, are you sharing your screen now, or?
Oh, yeah, I guess I am.
Yeah, so that they can't be able to see the board. That's maybe why that got dropped off.
Oh, sorry.
They may be able to click on it. Actually, I think you can click on the camera even. Screen share.
Yeah, I think it's doing all right now. Better be. So here we have two forces, F0 and F1, and that's when I applied these for heat. Now, here are these two forces in the second unit, so I'll have a different value of force here.
Right,
and
so
that's
a multiplicator unit conversion.
Right, that's right. So this is C is my conversion from mass from the other one, and D is the conversion of acceleration. Say, okay. Now, if you look at the quotient F1 over F0, this is unitless, and so this should be M1 over M2, and that should be E to the. I really should have rethought the way I did these indices, but whatever. This is E to the A2 minus A1, right? Now, this should be this unitless quantity should be the same in unit system two. But what I get here, this is again, actually, I guess this is M2 over M1, isn't it? And this should be M2 over M1. But this time it's E to the D times A2 minus A1. Now notice the coefficient in front of the exponential is the same. That's because that first bit made good sense. The mass 2 over the mass 1 is unitless, mass 2 over mass 1. So far we've got a match. But here, if we assume that D is not 0, and I don't think it's realistic to expect unit conversion to take acceleration 0, if D is not 0, then the only way that these two are equal is if A1 and A2 are the same, right? So what happens is physics is different in different unit systems. So there's something wrong. This is not very consistent. This is basically the linchpin of unit analysis is the fact that when you change your unit system, your unit quantity should be the same. Let me take a little side note. Here's another thing. So there were lots of people protesting F equals M e to the A. And of course, we see that we should agree with this. And a good physical thing is you don't expect the force to grow exponentially with acceleration. Here's another thing to consider. That's another way to write the exponential e to the A. And you can see in this particular circumstance that units would be extremely problematic here, right? I mean, that's just right out. So, of course, there are important unitless quantities that one encounters. So, for example, if you have in science classes, of course, E and pi, these are both constants that come up unitless in a lot of famous formulas like area of the circle and so forth. But pH, for example, specific gravity, things like winning percentage, the ratio of the mass of the electron to proton, these are all important unitless things that may come up in a lot of problems. Of course, there are things that do have units like Planck's constant, speed of light, the elementary charge, the gravitational constant of the universe. These are all things that have units. Here's another couple of applications here. Here's another one. Anybody remember how the average value function on this interval? You might remember. Well,
You integrate it over the interval and divide by b minus a.
okay. I taught calculus a ton of times, large letter calculus. It does involve this. And actually, there's something that goes in front of it. And a common mistake is, well, one mistake would be just to leave it like this. But one mistake I see a lot is this. Okay. And of course, this is not right here. Actually, this is equal to How can you help? Right, so I've got some wayward calculus student who's splitting like they're at the free clinic because they're worried they got their average formula wrong here. Right, they can't remember is it B over A, B minus A, or how could you help such a distressed person? Units. With units, right? The average value function should be whatever in the heck the units are on the whiteboard, right? But what you're getting is an average value along here, right? So we'll think of this as a length just for convenience, right? So the average value should be in inches, whatever, how high this is, agreed? What would the units on this be? Well, the integral from A to B gives you an area, right? It's this limit of sums in each one of these. So this thing right here, just the integral itself is in square inches, right? What's the units of this? It's cubic inches, right? Because B minus A is inches, square inches is cubic inches. Can't be, right? Because the average value of the function needs to be in inches. What do we have right here? We have square inches divided by inches. So at least I know this one is the better candidate because its units are correct. Everybody okay with it? You can do this. Let me give you an example here. A four-dimensional sphere of radius r. Now, just thinking about, by the way, I'm going to get a picture of this, right? Anybody have an idea how to figure out how to do this? And volume is the four, here, what do I mean by volume? I mean the four-dimensional analog. What volume is the three dimensions. Just for giggles, the way you would do this is actually, go home and do this problem. It's fun, and I'll tell you what the answer should be. How do you do a three-dimensional? You slice down, say, the x-axis, right? And every cross section is a circle, right? So you go, so for three-dimensional, then it's the integral. We'll go from 0 to r. We'll double it because I'm a lazy man. And it's pi r squared dx, right? Because every cross section has area pi r squared. And my only problem now is to get r in terms of x, right? And I can use actually the circle to do this. This is actually capital R squared minus x squared, and there you go. All right. What do you do for a four-dimensional sphere? You do the same thing, except now the cross sections are three-dimensional spheres. So you use your answer from here, instead of pi r squared, you've got 4/3 pi r cubed. And it's essentially the same problem. It's not very difficult to do, right? Even though I would, yeah, there's not enough pink there in the world for me to be able to picture this, but I can figure out what its volume is just by doing that slice, right? What is the answer to this? Well, I know something about units and symmetry. Here's what the answer is, a little facetiously. Alpha R4. End of story. That's the answer. The only question is, what's alpha? By the way, you know what alpha is? Fine. It's actually pi squared over 2. So go home and see if you can figure that out. That's the volume for the sphere. But you can use unit analysis just there. I mean, this is kind of very primitive. Gets me, I know what the form of the answer should be. right? So I can do all my fancy calculus, but something, it's gotta come out to something like that. Right? Here's another, yes,
Is that pi square over 2 related somehow to the sum of the reciprocal of the quadratics? Of all the squares?
I don't, here's what actually happened with Higgs spheres. So the volume started with circle. So it's pi squared, then for the circle, and then it's 4/3 pi r cubed. Pi squared over 2 r to the 4th, and it's something like, I don't know, 5/18. There's a 5 somewhere, but it's also some rational number times pi squared, r to the 5, the next one, and the next one jumps up to pi cubed, then the next pair are pi cubed, and it's so forth. So, and it basically, what these things turn into is integrating, doing the odd case like this is always easy, because what you have here is you have an even power of the radius. At the ones where you do the 4, you've got the odd power of the radius, and you actually have to do the square root. So there's a trig substitution, and every time you do that, you have to do that every other time it kicks in pi. That's essentially, that's fast and loose, but that's what happens. Okay. Other questions? So, right, you can use this to kind of ballpark lots of things. If you forget how to do things like arc length, surface, volumes. You can ballpark the answers, at least with regard to the units. And if you don't remember how the integrals work, it's like, oh yeah, I need that extra square root thing under the radical, or I need that extra square root thing under the integral sign to do it. You can remember this via unit analysis. Here's another one.
You know that the particle physicists will set C H bar equals 1. And when they get their answer, they just multiply by the appropriate units.
Yeah.
Right. C's and H bars, you get the right.
Here's another. Do you remember those old problems that you may have had in calculus or maybe in differential equations where they always here. Oh, you've got this big tub full of water, and there's a certain concentration of salt in this, and it's some initial here, and then it drains out at this rate. And you know what? Give an equation for the amount of salt in the at any time. This is really, if you take apart those differential equations, it's really just unit analysis. That's all you're doing. I mean, basically, all these problems are like unit analysis and common sense. Salt, change in salt is salt in minus salt out. That's it. I mean, that's common sense. And then everything else is basically doing unit analysis. And then solving a differential equation. There's that. But these things are usually small differential equations. Here's another kind of interesting sort of semi unit analysis. It was actually in well, it's in the ancient world. You know, it's actually kind of amazing because I think there are more people right now at this point in time that believe the Earth is flat than have. There's a large number now than there was in 1850, right? And of course, there's the old story about, you know, Columbus thought he was going to sail off. I want to prove the world is round. Bugs Bunny did that just fine, actually. Columbus, I don't think anybody really thought at the time that the Earth was flat then. And actually, in ancient, I guess it was ancient Egypt. One of the ancient, I'm not so good at the history. But in ancient times, they figured out that the Earth was round and actually got a good. They got a good feel for how large stuff. They're actually fairly accurate. Do you know how they how they discovered, what the radius of the earth was.
With the shadow, right?
What's that?
Was with a tall building, well, not a building, but whatever, and then measuring the shadow, right?
That's right. So, I forget what city it was. It may have been Alexandria, I'm not sure, but anyway, this famous dead guy, noticed that on a certain day in summer, when the sun was right overhead, it shone straight down this well that was in the middle of the town. So he got, he paid somebody to pace off the distance to this other city and stick a stick in the ground and measure the shadow. Right, which if the sun's coming this way, then the shadow would be parallel. Right there. So, of course, there's a little bit of curvature here, a little bit of error. But if his stick was L and he measured the shadow S, then I guess what is it? S over L, well, the inverse tangent of S over L is equal to theta. Right? And of course, that's the same here. And he used that. And so he gets this unit, this quantity. So what he's going for is R, and that is d over theta. And this bit right here is unitless. And actually, even way back then, I mean, I guess the guy had to pace off the distance and record that carefully and measure as carefully as he could. He got the radius of the earth very close, especially given the fact that he's not even a calculator to what the radius of the earth is. So there's a lot of things that you can do with kind of common sense and close to unit analysis. So let me get to the story at hand. Let's see if we can figure out what Sir Geoffrey Taylor. Yeah.
Do you think that they really calculated the inverse tangent, or is it such a small distance that they just separated?
Yeah, I mean, because the guy wasn't. There's no way it was that angle, right? I mean, he wasn't pacing that long, right? End up in an ocean or a swamp or something. So I'm sure the angle. That's probably right. Probably. That's what we would do now. They probably did something a little bit more primitive. They still got it pretty close to right.
Can you make a small lines approximation? The arc can. Speed. That's what you're saying. That's really wrong.
Well, so if it's small enough, right? Because the inverse tangent of zero is zero, right? So yeah, but well, remind me. We'll look at the power series of the inverse tangent, see how good it is. It's not going to be as good as power series for sine. So yeah, because the power series for the inverse tangent is going to it's going to have radius convergence 1, I guess, for the inverse tangent of x. So all right, so you all saw my stills movie, right, with the scary nuclear bomb. So let's see if we can get some of the players in here. I'm going to make some assumptions. These are some of the assumptions that were made. One, that the energy was released essentially from a point, right, to some point of space. Kind of idealize that too. And I'm going to make another assumption, and that is that the shock wave is spherical. And of course, as the explosion rumbles out, that assumption is going to fall apart after a while. But if you look at the time scale that we had in those pictures, I mean, it was very, very small fraction of a second. I think it was like a hundredth of a second, apart in the two pictures that I had. And so maybe this is somewhat reasonable to assume that it kept a spherical shape in that bit. So what we want to do, and the idea is again, playing towards sort of balancing the units. That's what we're going to essentially do, which is equivalent to like looking at a unit that's constant. So let's elect some candidates here. So what are some relevant things? Okay, let's imagine that we're Sir Geoffrey Taylor. We're trying to figure this out. And of course, his big goal is he wants to make the government mad by figuring out their big secret, right? So I'll get it started. He wants the energy, right? He wants to know the energy. What are some other relevant variables that we might consider? Too much is better, because if we get like a variable like, number of T-Rexes in the pond, we can ignore that if we decide it's useless.
Radius?
What's that?
The radius?
Okay, yeah, radius. Shockwave radius. R. What else are relevant? Yeah,
Who stamp on the video?
there you go. How about time? I think actually you guys have kind of helped us figure this out. I think there's one more we're going to use that might be a little bit.
Did you estimate right?
I'm sorry.
You estimate that's because you get blow a bomb up, it's not the size of the city. Right?
Yeah. The mass of what? The bomb itself.
Yeah, these fissionable material.
Oh,
But they didn't know anything. This guy didn't know that this was E equals MC squared type stuff.
yeah.
Converting mass to energy. He didn't know that in his calculation.
Well, I think he was actually at the Trinity Test.
Oh,
Right. I think he was actually at the test and then saw the movie later. But I read that on the internet, so I can't possibly be wrong, can I? But that's one thing. But I think he actually didn't use this one. But there's something else that's this one's a little bit more subtle. Right? Yes.
Would you need like air pressure or air density?
Okay, there you go. Right. I mean, if you explode this thing on the moon, if you explode this thing in the atmosphere, if you explode this thing in the ocean, it's probably gonna be different. So we toss that one in. And this is going to be the density of the medium, which in this case is just the atmosphere. Our case, air. Okay. So these seem relevant. So here's what we're going to do. We're going to try to do some. Well, first of all, let me break this down. So let's do some more forensic breaking down. The units of energy, I'm gonna put in terms of, uh, do that, let me do this. So I'm gonna bring out some basic. We'll say, so in particular, length is gonna be one of our basic units. And R is length, right? So R is this unit. Time. And also, mass. Yeah. And so I would couch the other step in terms of this. So the energy, well, the units of energy are like mass, length squared divided by t squared, right? I agree with that. And what else going through? Oh, yes, the density. The units of this, it's the density of medium air. It should be in mass per cubic length, right? Time is a player, and R is in units of L, as we pointed out before. And so, what we're going to do is we're going to make the assumption that R is a function, and a simple function, because whenever you want to try to model things, always start as simply as possible. Energy to the x power, d to the y power, and length to the z power. And k here is some constant of correction. So and I'll assume it's a unitless constant. Okay, so let's have this very naive, simple model. And this is good because powers are very good at doing this kind of unit preservation. Now, let us compare say basic. And this gives us a small set of equations, just like being in linear algebra. Everybody's favorite. Compare L appears in the first power here. Do I agree with that? Because this is just a flat out L, right? That's unitless. Okay. How many times does L appear in E? Twice. So I got a 2x here for its appearance in E. It doesn't appear in time at all, right? And how many times? How does it appear in? Oh, I think I've got L. I copied that down now. There's something on here. Oh yeah, of course. This last bit, of course, is rho to z. There we go. I'm playing with the medium now. Okay, so there's no L in time, but how many L's are there in rho? -3. Everybody agree with that? So this should be minus 3z. Great. Compare heat. Well, we got, go through the same process here. There's no time unit here. In E, let's see, I'm gonna get a -2 again, so this is -2x. Actually, this is supposed to be. Oh, let's back now. There we go. This is -2x, great. And this is 1 or plus y. And in the row, there's no time, right? So we just got that. And let's compare M. No M over here. Unitless again. Okay, so there's 1 M in E, so that should be X, right? And in T, there's no M, so it's 0 for that. And how many we've got? Let's see. Everybody agree with my equations? What's that?
3 equations, 3 unknowns.
That's right. So this is just like go up your output, right? And so actually I can use these two to eliminate. So I'm going to multiply this by -2 and add it to this. So I get 1. That's going to be 0 minus 5 6. So Z is -1/5. Agreed? And if that's the case, then this equation gives me that X is 1/5. Right? And Y is 2/5. So we get this naive estimate. What do we have? Energy is equal to K times E to the 1, or yeah, E to the 1/5, or I'm sorry, R. E to the 1/5, T to the 2/5, and M the -1/5, if I remember right. Right. Or
No,
I'm sorry,
row,
not
row.
row. I keep doing that for row.
Yeah, row in kilograms per meter cubed, then row is approximately 1. Wanted to do make the units easy.
So I can massage this. And I'm just gonna, I'm gonna take the 5th power of both sides and I'm gonna call this K 5th alpha. Over. And so this gives me E is 1 over alpha. R to the 5 rho over T squared. Now, here's the naive thing that got up with. Now, what Taylor did next was based on experiments and things about gas stuff or whatever. He said, well, K is about, well, actually, it turns out I think it's about 1.041 or some business like that. He said, well, let's look at KB1, right? Which physicists like to do, right? So that's about 1. R was 80 meters. Rho was about 1.2 kilograms per cubic meter, about 1. And T was about 0.006. So we got doing this calculation, like 1.1 times.
That 0.006 seconds.
Oh, 6 seconds, that's right. He got,
So 6.
yeah, 6,000 a second. So he got 1.1 times 10 to the 14th joules. And now 1 joule is about 2.39 times 10 to the negative 13 kilotons of TNT. So when he converted the joules he got, 1.1 by 10 to the 14, to his kilotons of TNT, he got about a yield of about 21.6 kilotons of TNT. And the actual answer, according to my sources, my government sources, are about 24.8 plus or minus 2 kilotons. So that's a freaking good shot. Doing nothing but basic unit analysis, some common sense perhaps, and assuming the K is 1. Okay, so anyway, that's kind of it. Any questions on
I do have a question.
Yes.
Back in college, I used to make dry ice bombs with a 2-liter bottle.
it? Oh, we did that all the time.
And
We did it with liquid nitrogen. We poured it in a
Right,
Pepsi
right.
bottle.
And it actually made a small crater in the ground, at about 3 feet long. So I was wondering if we could estimate the yield of dry ice bomb.
Yeah, I guess we probably could. Did you get it on film?
Did not get enough. That's the issue.
Yeah,
Yes.
so this final calculation, this done using just one of the 2 pictures you showed us, like you just need one moment. I think.
Yeah, that's all he really needed, right? Because so under his assumptions, all you really need is one reading this, and the
I
time.
wonder how, you got 2 snapshots there, how different they are.
Well, I think there were actually more than 2 snapshots that were released to the public. Yeah, so they had the movies there, I guess for propaganda purposes. I'm not really sure. But I think there were actually several snapshots. There were some, because I've seen some that are later when you can tell that the explosion is starting to lose the spherical, it's getting kind of fluffy or something. Yeah. Other questions? All right. Well, listen, you guys have a good weekend. Next week, Neil Calkins here. So mark your calendars. Neil's always got something up his sleeve. So be there for that. Have a good weekend, and we will see you next Friday, I hope.